Okay, we move to the next chapter, that is the circular motion. All right. So first we'll look at what is circular motion, right? So circular motion is uh, the motion of an object in two dimension, and the motion is on a plane. So this is basically, it's a type of two dimension. So I can write it's a 2D motion, or I can also write the motion in a plane structure, right? The plane may be horizontal, inclined, vertical, doesn't matter what is the orientation, but object moves on the surface of a plane and in a circular path, right? Now the fundamental idea is that whenever an object moves in any direction, the velocity of the object will be along the same direction in which it is moving. But now you see, at every moment, whenever an object moves in a circular path, its direction is going to change continuously. Because of that, in case of a circular motion, the direction of velocity keeps changing continuously. So even we can say that the speed is constant, velocity keeps on changing. We say that, okay, the speed of the motion should be something like, say, 10 meter per second. But you see that the velocity keeps on changing because velocity is a vector, its direction keeps on changing all the way, right? So normally that means since the velocity keeps on changing, we cannot write v is equal to u plus at, the normal equation which we had used in the motion along one dimension. Right. So our first objective is to look at the what happens with the velocity. Right. Fundamentally, in a circular motion, we have two types of velocities. First one is called as the angular. First is angular velocity, and the second component of velocity is the normal linear velocity. Okay, let us try to look at one by one. So we'll start with the angular. All right. So the angular velocity, let's try to define that with the help of a diagram. So this is the circle. This is the center of the circle. All right, let me draw the x and y axis here for our reference. Okay, so this is x axis. This is y axis. Okay, now let us mark some other points. One here and one. Okay, so initially let us say there is an angle theta and there is a small angle change. The change in the angle, we shall denote that as d theta. Okay, so this is P and this is P dash. Okay, right? So d theta, or I can even denote it as delta theta. Right? Okay, now let us consider, I'll try to explain what is there in this particular diagram. All right, let's say that there is a particle P moving in a circular path. Okay, let us say the radius is r. for the circle, and the circle's center is O. Fine. The position of the particle P at a given instant is described by the angle between the OP and OX, right? Where is the particle right now, right? At what location? Because radius is fixed, right? In order to identify the location of this particle P, right, I just have to tell only one parameter, that is theta. Theta is equal to 90 degree means you will understand that, yes, the object is here, right? This is for 90 degree. So angle is the parameter which tells you the location of the object at any given point of time, right? So theta is the one which decides that. Now, if I say theta is equal to 120, maybe I'm going to look for the particle somewhere here, right? And so on. 180 will be the horizontally opposite side. That should be somewhere here, right? 270, if I say, you will search here, right? Like that. You see that theta will define where is the object. So the theta is called, there is a specific name for this theta. Let me write that. So here the theta is called as the angular position of the particle. Angular position of the particle. All right, fine. Now, as the particle moves on the circle, its angular position theta keeps on changing. Suppose if the point moves by an angle delta theta or d theta, right? In the time taken to make this moment, right, from P to P dash is dt. Small angle change in small time, right? Then we can calculate the rate of change of theta, because normally you see object was here. Sorry, I'll write a different way. If it is linear motion, right, object was say here, it moves to this location, right? So let us say I'll try to call this as x. This is x dash, so that this distance is dx. So right, and if it takes a time dt to cover that, dx by dt itself is the velocity, right? So very similarly, now the position is identified by the angle. So change in angle per time will be the angular velocity. So we'll try to define that now. Therefore, the angular velocity. How to define angular velocity? The very common notation is omega. Omega is equal to so this is d theta, change in theta per time, right? Small change d theta per small change in the time. Time taken to make that change will be very small, so that is dt. So d theta by dt is called as the angular velocity. If you are able to write an equation for theta, differentiate that with respect to time to get the answer. Right? So omega is the angular speed, right? Or the magnitude of angular velocity. As well defined, the velocity will be a vector quantity, and this angular velocity is also going to be the vector quantity itself. So the direction of omega is always perpendicular to the plane of circle, right, given by the screw law. So for example, let me try to mark this point. If this object is moving to the left, you can say that just one hold for. Okay, continue. We were trying to identify the direction, right? What will be the direction of velocity? We'll try to mark that using another example. Let's try to consider two cases. So this is the one of the path of the object. Let's consider another one of the same type. Okay, this is the second path. If at all the object is moving, let's say in the clockwise direction, so at a given point on the circle, on its path, the direction of the velocity will be right? Let's try to mark the velocity. At this point, it is a tangent drawn at that point. So this is the direction of velocity. Let me consider another motion. This is anti-clockwise. So if we have an object located here, we can mark the velocity in this direction. It's a tangent. Okay, now that's a concept related to the angular velocity. Next, let's move to the normal velocity, which is a linear velocity. So linear velocity, we already have defined that. So let's just write an equation. So velocity is equal to ds by dt, where s is the distance covered, right? Even we can write this as some of the books will say this is dr by dt, where r is the distance covered. Okay, using this, we can try to write the linear velocity at any point of time. It's a normal equation. Right. Now, let us try to give a relationship between the linear speed and the angular speed. So in order to identify the linear speed and the angular speed, we will consider the same diagram which we had written over here. So let's come back to this. I want this diagram. Okay. Now, let us say the distance traveled by the object is pp dash, but pp dash is not straight line, it is a curve. So when you have the curve, we want to measure the linear distance pp dash. So I'll just write the linear distance pp dash is equal to, use the fundamental concepts of trigonometry, right? Let me denote that pp dash is, right, denoted by, let me say that that is delta s, small distance, is equal to, right, if you want to measure that, it is radius into the angle, radius into angle. So radius is r, and the angle made at the center of the circle when object moves from pp dash is d theta. So the angle is nothing but d theta. So we'll write r into d theta. So delta S is equal to R into d theta, or I can actually write it in a slightly different way. Let me make this delta theta so that I differentiate. Both sides will become the ds on left side, d theta comes on the other side. Okay, so for that reason, I'm making a change. Let me write this as delta theta. So if I try to take limits on both sides, so that is limit delta t tends to 0. This is delta s by delta t should be equal to, once again, r into limit delta t tending to 0. This is delta theta divided by delta t. So the left hand side is ds by dt, right? Because that's the definition of derivative, right? Limit delta s by delta t is ds by dt. Similarly, r is a constant. Limit delta theta by delta t is d theta by dt. Right? So we know that the relationship ds by dt is velocity, normal, linear velocity. R is the radius. D theta by dt is omega. Right? So we can relate the linear velocity to the angular velocity by using this equation. Right. Let's move ahead. We move on to the next topic, that is what happens to acceleration. Right. In this case also we have fundamentally two different types of acceleration. One is the angular. angular acceleration, and the second one is linear. Right. Now, as per the fundamental definition, acceleration can be obtained by taking the derivative of the velocity. So therefore, if at all I want to measure the angular acceleration, so first let's discuss about the angular. The angular acceleration is denoted by alpha, which is d omega by dt. So d omega, omega is already measured. Omega is equal to d theta by dt. So this becomes d square theta by dt square. Now, as we know now, velocity was vector quantity, derivative of a vector is once again vector. So you have acceleration, in the sense angular acceleration is also a vector quantity. Right. Now, uh, let us try to measure. Okay, let's try to look at the various components of acceleration. Okay, various components of angular acceleration. Right now, in a circular motion, linear speed of the particle may or may not be constant, but the direction of the velocity will be changing always. Right. So, which means the velocity is continuously changing. Therefore, acceleration cannot be zero in this case. Even the object is moving with a constant velocity, acceleration is not a zero. Right. So, the acceleration can be divided into two components. So, this angular acceleration has two components. Right. They are, the first one is called as the tangential acceleration, and the second component of the angular acceleration is called as the radial. As the name suggests, tangential is tangent to the direction of motion, radial is along the radius of the circle. So if we have, okay, let me draw another diagram to understand. So this is the circular path in which the object is moving. That is somewhere here. Okay. Now, the tangential components could be along any of these direction. Direction we cannot identify as of now directly, right? This particular, either this or this, any direction, this is the okay, let's give a notation. This is alpha t, okay? Or this could be the alpha t. So tangential is alpha tangential, and this is alpha radial. So radial, again, the radial direction could be anywhere like this, right? It can be towards inside or outside. So I'll slightly try to drag this so that this is alpha r, or this can also be alpha r, right? It can be into the, towards the center of the circle or away from this. So we have components like this, right? The component of the linear acceleration in the tangential direction is called as the alpha t. So how to find out alpha t? Alpha t is very straightforward. So alpha t can be simply calculated from the normal velocity, that is dv by dt, right? So we had a velocity component, linear velocity, differentiate to that to get the alpha t. Right, but this is the fundamental equation, but we'll slightly modify this. We know that alpha t is equal to d, velocity is nothing but it is r omega divided by dt, right? Here r is a constant, r times d omega by dt. What is d omega by dt? D omega by dt itself is the normal alpha one. So this is r into alpha, right? So I can write alpha t is equal to r times alpha is another important equation. right? Then we can also understand one more a very important point, that is the component of a linear acceleration in the radial direction towards the center is called as the radial component, or it's also called as a centripetal acceleration. Let me write one point here. Radial acceleration. So this can be measured as the component linear component of linear acceleration in the radial direction is called as the radial acceleration is radial, or it's also called as the centripetal. Right? So this component is responsible for change in the direction of the linear velocity, right? So this component is always there, always whenever an object tries to rotate in a circular path, there is always a force that is attracting towards the center. There is an acceleration component towards the center of the circle, because of which there is a continuous change in the direction of the object. Right. So let's try to calculate this. This is alpha r, alpha radial. This is equal to the equation v square, linear velocity square, divided by r. But the v is nothing but this is r omega. So r omega whole square by r. One of the r will cancel. So this is r omega square. Okay. Now let's look at another very important relationship. Let's try to write the xy coordinates first. All right. Let me say this is the tangential component, that is alpha r. So the radial component will be perpendicular. So this is alpha, that is alpha r radial, alpha. Let me change. Okay, fine. No issues. Alpha r is this, alpha is this. Let me assume that the alpha comes in this direction. So the angle between the tangential component and A, right? So this is A. Let's say this is denoted by the theta, right? So I can actually write now from the fundamentals of vectors, this is A square is equal to, this is alpha t square plus alpha r square under square root. So that means I can simply write the first component. The tangential component is dv by dt, the whole square, plus alpha r is nothing but I can write v square by r, the whole square under square root, right? So this means I already know that dv by dt, we already proved that this is r into alpha. So this is alpha r whole square, plus the second component we just proved that this is r omega square, the whole square, right? So under square root, right? This is the equation which we can, right, use to calculate a square. So a can be found using this. I made one mistake. This is not square. This is a. A is equal to, because a square is equal to the square of vertical component and horizontal component. But a means this is the equation. Okay, please correct. Now, this also implies that if I want to find the tan of this theta, tan theta is equal to alpha radial, right? Because opposite divided by the adjacent. Adjacent is alpha t. So if you want to calculate the theta, then you have to use tan inverse ratio and calculate alpha r divided by alpha t. That's all. The components of A related to A, right? What are the components of A? Alpha R and alpha T. AR and AT, that's also fun. Okay, let's move ahead. Now, so types of circular motion. Okay, so for a time, there are three different types of circular motion. So the first one is the uniform. It's called as uniform circular. Right. In this case, the V and omega, they are constants. Right. In such case, what is alpha t? This becomes 0, right? Because V is a constant, equation of that, right? Alpha t has R into alpha, so that becomes equal to 0, right? dV by dt, V is 0, V is a constant means dV by dt is 0. That's why alpha t is equal to 0. So this means what happens to omega? Omega is equal to a constant, right? Now, V is a constant because of which alpha t becomes 0. When alpha t is 0, omega becomes constant. So this means the what happens to alpha? Because you see alpha is equal to 0. So what happens to A? A is equal to AR. A is only one component, that is AR, which is V square divided by R. Otherwise, you can also write R into omega square. Only these are the equations we have to use whenever we try to uh, discuss or solve the problems about uniform circular motion. One thing to remember, V and the linear velocity and the angular velocity omega, they are constant. So substitute these equations in these values in any of the equations we got earlier, we will get the equations corresponding to the uniform circular motion, right? So what happens now? What is the direction? A is always towards the center and V is tangential uh, to the path of motion. This is what we already know anyway.